Some prescribe that to us.
Yeah, okay. I'll get doctor notes. I should buy some doctor notes and
I have
sign
an
them.
uncle in India. He gave me some. Don't worry.
Dr. Regularity will always write your doctor's note if you want.
Yeah, one time was like, yeah, prescribe guys caffeine.
Okay, so we're kind of switching gears, so a little different than what we're used to. But we're going to kind of quickly talk about something, and then we'll get right into it. So when we look at differential form, or differential analysis, it basically determines P, V, T, rho, etc. everywhere in the flow. Okay, so we talked about linear momentum before with forces, right? We had water shooting at like a plate, or we had shooting out of a rocket or whatever, okay? That is using linear momentum to find forces, external forces, or the speed. But it never really gave you the full details about the flow everywhere. Okay, and you definitely need this. In my case, I needed it, right? When I looked at the contours of the inlets and how the flow goes inside the aircraft and how I do that. So there is a need for this. Okay, a lot of the times, if you're not really doing research, you won't need a whole lot of this, but this is very important, especially if you want to know the details of the flow. Okay. So what we need to do is we need to look at conservation of mass in differential form and momentum. Okay. So let's kind of talk about conservation of mass. All right, so write this down and I'll go through it. Yes.
It goes from the control volume to what?
This is, actually I could write that, sorry. I'll explain this here. So I kind of brought everything to the other side. If you think about this, this right here, what is rho times V? It's mass, yeah, and then divide by time, you get mass flow rate, right? So basically, this is your mass flow rate. Think of a tank. Remember that we had that tank that was emptying? Okay. This right here is the mass flow rate of like the tank. Okay. And then here is what's coming out and coming in. Okay. So instead of writing like just a simple m dot here of the control volume, why do you think I have an integral in partials? Because the density could change of the substance, because it could be air or it could be some sort of gas.
So why would it change if like we're just using it for a certain control volume? If volume is controlled, it shouldn't just be.
But if you consider the water in the tank, your control volume, not the tank itself.
So instead of doing water, we know water is incompressible. So you could change that to m dot, right? But if you had air in there, and say you had this container and then you started filling it, okay, the density of the air inside could change over time. Okay. All right. So think of a good example would be a air compressor. Right. What happens to the density of the air in an air compressor over time? It would change, right?
Yeah.
So you have mass flow rate coming in, or you turn it off, you flip the other switch, so now it shoots out, so the density changes. Okay. So this is a prime example of conservation of mass in the air compressor. Okay. Does that make sense now, Andrew? All right. So, well, in order to actually get the correct mass, you have to integrate. Calc 3, did you do that? Well, I know you did integration, but did you do anything where you had like a cube? I can try to get some information on this. And you wanted to actually find the mass, you would actually have to integrate the density times the change in volume. Okay, that's why you have the integral, to actually find the total mass. All right?
I think we did, it was 2 years ago.
Yeah, okay, all right, that's fine. So this, I just switched. You could do, this is what they call the control surface. So on the left here, underline is your control volume, so inside. And this is actually what's happening at the surface. Okay. Instead of doing the integral, I just kind of made it easier for you to look at. It's just basically mass flow rates coming in and going out. Okay. So on the left, it's your control volume, mass flow rate, and on the right, it's what's happening through and out of the surface.
So you don't have to use the integral on the right.
I'm not going to do it that way. I'm going to do it this way. Okay. But theoretically, you would have to do the integral. Yep. Yep. Does everyone understand this? So what I'm going to do is I'm going to break this down into differential form to get the equation on the top here, right here. Okay? So you take the basic equation that you kind of know, and then we break it down into smaller increments in differential form. So what we're going to do is we're going to draw a box. Well, sort of a box. Cube. Oh, come on, why doesn't that do that? And let's do purple. They're all supposed to be the same dimension. So it's a cube, but in differential. So we're only looking at the small little cube in this big, say we take this room, we take a little cube in here, okay? So what we need to do is we just look at a small change in that. This is how we actually do the derivation. So what we're going to do is look at the x direction. So let's do blue. So we're going to derive the conservation of mass on this cube.
Why did you highlight the side wall?
Because that's the x direction. I'm going to show you the x direction first.
Bottom of the x direction.
No, x is this way.
Yeah, I thought on the bottom surface view. I don't know why the left sides are.
The bottoms would be the y direction.
It's kind of like the walls.
And then in this direction is the z direction.
Yeah, okay.
Yep. Yep. Okay. So that's m dot in the x, and that would be m dot out in the x. So x direction. So what is the equation for m dot? Rho AV, right? Okay. So rho U times dA. So why did I do U?
That's velocity.
That's the velocity in the x direction. Okay. Why did I do dA, not just A?
Because the air is changing.
Because, yeah, we're looking at an infinitesimal small little section, and the way we do it is we just put the D in front. Okay. Can someone tell me, can you break down dA in terms of those three or two, I guess? What would it be? I have dz times dy.
Oh, yeah.
Right?
Yep. They actually have.
Everyone okay so far? Questions? All right. So how about m dot out in the x?
It'd be the same thing.
Slightly, it'd be slightly different. Let me write it and explain. Bless you. So, did I write that right? Rho U dx. Yep. So write this and I'll explain what's happening here.
It's not slightly different.
It is slightly different.
Slightly.
Yeah, I feel like one extra variable.
I'll put it slightly. So think of, let's do this first. If we're here, say this is x1, how would you find this x2 if you know what x1 is and this? You would add them, right? So it would be, to find x2 would be x1 plus dx. Okay? So here, we know what the mass flow rate in is, and you add, if we cancel these dx's, what do we get? Delta rho u, right? So a change in some sort of mass flow. You see that? Does that make sense
Is the
now?
mass flow rho AV?
Well, it is. I just took it out.
We're just changing the change in density and velocity, right?
So it is. It's rho u times this, and then that times that.
So what you're saying is that through those walls, there's mass coming in and out. There's no like.
Yep.
Okay.
Yep. So in order to get the next mass flow rate out, we take the original mass flow rate and we add a small increment of mass flow. This change in mass flow. Okay. And the way we write it to get a differential form is we have to put it in this form right here. Okay.
Wouldn't you get a volume there if you distribute a dy dz to the second term in the parentheses? Like dx.
Well, you assume this and this would cancel, so you get a change in mass.
That doesn't partial.
Yep. You could write these as partials and partials. That's fine. Okay. But they are still a change in x, so they would cancel. Okay. So just think of it the way that we talked about it before. In order to get x2, you add x1 plus a change in x. Here we're talking about mass flow, so we take the mass flow coming in, we add a change in mass flow. But the way we write it is we have to put this, because this is the correct way we would actually get the equation that we want. Okay?
That's because we assume the box is expanding.
Box is expanding?
We assume that there's a change in the fluid in the box.
Oh.
Yeah. Okay. How about the y direction? Try the y direction. What would m dot in the y direction look like?
Rho u dA.
It would be rho v. Yep. Dx dz, right? Okay. How about m dot out in the y? Slightly different, right? But it's just rho v plus du, partials, Yep. I know some of you may never ever use this, ever touch it again, but this is how, if you're going to get into research, you're going to go to grad school, or you kind of want to know how this stuff is derived, this is how they do this right here. Okay?
Are we making an assumption that gravity is not acting on this fluid at all?
We're only doing mass.
Oh,
We have not done momentum yet.
No.
We do momentum the very same way. Yep. Yep. What I might end up doing is briefly talk about that, and I have a video that I can just show you if you want to watch more details. All right, we'll do Z to be completeness for complete. Rho W dy dx, and m dot out in the Z is rho W plus rho partial Z rho W dz and dy dx. So just remember, just kind of think of it in simpler terms, but we have to add these extra things in here to be actually complete in our analysis.
But you change up the velocity variables.
I did on purpose because the x direction is u, the which way is y, up. Yep, that would be v, and then coming in and out of the page is w. Yep. I can go up. Right here?
Yep.
Yep. Okay, so what we need to do is go back to this right here. The red equation up top. We have m dot out and m dot in. What do you think we need to do? M dot in is we add all these, right? And m dot out, we add all these. Okay? So I'm not going to do the whole thing. I'm just going to show you. So step one is m dot in is m dot in x plus m dot in y plus m dot in z. And then we do the same thing for out. I might as well write it here for completeness. The way we do this is we just say, okay, we ignore the integral. We just kind of do it this way. Yep.
Oh, I didn't even notice it.
Yep.
That makes sense.
Yep. Bless you. Bless you. So we have now the terms, and what we do now is we combine them. Let's go back up here. Can you still see that? So what do you think is going to happen? We have minus m dot in, right? So some terms are going to be negative. These are going to be negative, 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 and you're going to add what? This and that term, and this and that term. And what's going to happen to those terms?
Cancel. You change up at the.
They're going to cancel. Yes. Yep. Yep. So you're end up going to get this.
Yeah.
After some algebra, actually it is algebra, you get this. You could try it at home if you want to, but it'll work. Yeah. Yeah, you just plug and chug and cancel. I guess so.
I just have no idea.
I don't know, to be honest.
There's probably some mathematician that would yell at us.
That is a funny looking row.
Dr. Greg, what do you
Yep.
mean by they're like why would rho U, rho V, and rho W cancel over just with a negative?
Because when you factor out this and that term, this would be positive, but this right here is negative. So we have rho u dx, sorry, dz dy on the in is negative, and you add it to this black term under here, that would go away. So you're just left with this term.
Oh, because you're looking at everything combined. Like
Yes, I'm combining everything because the basic equation is the negative m dot n. So on every term, you're only going to get this, and that other term. Okay? And look, dx, dy, and dz, they do what? They cancel too because they're on dx, dy, they're on every term. Okay? So you're left with this, and this is our differential conservation of mass equation right here. Okay? It accounts for the change in density with respect to time. Because why are these in parentheses here, and why isn't the rho taken out?
Because the
Rho changes.
Because rho could change with x and t, and u could change with x. You know what I mean? Okay. Questions? As long as you understand kind of where this comes from, that's all I was trying to get to, okay? Because you're going to use this next equation here multiple times. So there's special cases. So that is the fundamental equation for a differential form for conservation of mass. Special case, actually let's just do one. Because we'll do steady, incompressible flow. What does that mean? Yeah. So does the density change in time? No. No. So what happens here? You can take density out, right? And then density ends up going away, right? So you end up getting this.
Steady flow and your velocity is not changing.
But not with time, but not with x, y, and z. They could be different. Yep. Now again, u, the reason they're partials is because u could be a function of x, y, and z. So here's an example to see, well, why do we use this? Well, if we say u is a x squared minus y squared, v, I'll just do little v, negative 2axy, and w equals 0. Tell me, does this velocity profile conserve mass? What does that mean? It may or may not. Why? What do we have to do? So a is a constant. Yeah. So what we need to do is we have u with respect to x and y. We have v with respect to x and y. So is this 2D or 3D? 2D, because that's 0. Yep. So we know it's 2D flow. And if we plotted all the values, you could get the whole distribution of u and v, right? We've done that before. You've done that a long time ago. Okay. Now the next step is to say, well, is this a valid profile? And what we have to do is see if it actually conserves mass. Okay. So let's see how good your partials are. This is ax squared, right? So take du dx. What do you get? 2ax. Yep. Yep. Okay, because we treat everything as constants. What about dv dy? Negative 2ax. So let's add them together just to show it complete, but yeah. So I took the equation in red up top, and that's the equation here. And they do. Boom. So this profile, if we plotted this, would validate conservation of mass, which is good. It has to, right? Everything has to. If it doesn't, then you have to throw it out. It doesn't work, okay? Questions? Make sense? All right. So this is, I think, the thing right on your first page here, conservation of mass. So every flow has to conserve, has to conserve mass. Okay, let's talk about the stream function. So very similar to stuff we talked about before, the stream function is a easy way to get streamlines, and we plot them. Okay, it's a simpler way than doing the old way. All right. So what we're going to do is we're going to look at 2D incompressible flow. So the conservation of mass in differential form is this.
Is that only one of the ways, though?
Say that again?
Is that only one of the ways, or is that the only way? Like, if you do it in the Z direction?
Yes, you could do 2D. It could be du. It would be dw dz plus dv dy. Sure. Yep. It's 2D. Yep.
Okay.
So I guess incompressible in xy plane. How about that? So what we can do is there's a clever way, which is the stream function, that we can make. We have like two variables here. We can make it into one variable as a function of x and y. Okay? So we need to define some things first. And we'll do an example. This is your stream function. I believe it's, I'm not sure, to be honest. Trident? I don't know, actually, off my head. Anybody have the vibration nomenclature?
Oh, yeah, that's pretty good. It is just like
We'll just call it the stream function.
That's psi.
Psi?
Yeah.
Oh, it is psi, yes, yes. Good. And guess what? If we find psi, different psi values are our stream function, our streamlines. So we're going to figure out how to find it. Okay. Yes.
Isn't the U's will have Vx and the V's will have
Correct.
Vy?
It is correct. Yep.
So is it changed now?
What?
Well, we're with stream.
No,
now.
but we're using stream function.
Oh.
Psi. Yep.
So that
Did you miss it? No, I'm just kidding. Yes. So we define u as d psi dy, and v as negative d psi dx.
I don't know why.
What'd you do?
I thought that was a 2.
No, partials. The partials.
I have to do it myself.
Wait, so are we doing specific velocity? Well done.
Oh no, I do that on accident. Sorry.
So many V's.
There is a lot of v's. I will let you know. My twos, I write like that.
I put the line through my Z. Yeah, I know.
Yeah.
I know how you write it. But
So yeah, my z's are this way.
yeah.
Same with sevens, and then my partials are that way.
You just read it better all that. I like how I can write a 6 just fine, but a partial looks like a person who's never written before drew it on my page.
All right, so here's an example. We're going to use the same u's and v's that we did before. So the homework question 3, I think, has a pipe, and it wants you to find the stream function of the flow inside. I don't know if it's water or air. I can't remember.
this is streamlines, not streetlights.
These are streamlines, yes. So what we're going to do is I just kind of said, well, we already know what u was defined as above and v. So now we have what the psi dy equals and what the psi dx are in terms of negative. You want to flip this so the signs are gone? So there's certain steps we need to do to find psi, which is again a streamline.
Just like theory.
Yep. Yep.
Great.
Step one.
Wait, Doc, why do you have the negative in the part of psi over?
Because that's what we define.
Goes up there. Oh, that's the original. That's how it's
This is what we've now picked u to be positive d psi dy and v is negative d psi dx. Yep.
Is that always the case?
That's always the case.
Okay.
Yep.
I just did negative.
Yep. And this is a kind of a slick way to find streamlines if you know your profiles. Okay. It's actually easier than trying to do the other method. Remember the other method? Where you had dx over x and equals dy over, dx over u equals dy over v. We had to integrate. Yep. Yep. Okay, so what did I call equation 1? I called equation here. This is equation 1. And this is equation 2. So step 1, do a partial integration of equation 1.
This is 12 for streamlines.
Yes, or psi, yep. So we're going to integrate, yep. So did everyone see what I did? I took equation 1 and I multiplied dy on the right, and we're going to integrate both sides here. So psi becomes a x squared y minus a y cubed over 3 plus f of x. Because it's a partial derivative.
Would it be like f of y? The greater degree with respect to y.
Hold on, it is.
Even if you function of y, then we have the function. You don't know. We'll be fine.
It should be a function of x. Why is it a function of x? Hold on.
So what is it when?
Yeah, it has to be. Yeah, it might not be a function of x, but it could be some constant or x in it. Because when you take the derivative, like what Kristen was saying, it would go away. Right?
Yeah.
Okay. So the reason why, okay, let's step back. Everyone understand why we add y here, and then this is y cubed over 3? Okay. Now, the reason we add this is because this constant could be a number or a function of x. Either one, doesn't matter. But it cannot have y in there. Because if we take the derivative of this, do we get this back if this was a y here? No, you get something new. Okay? Good. Yeah.
Exchange partial derivative of psi. There's no other size in the equation to like everything is 0.
No. I'll do this in purple.
Because it seems like you just took an integration.
So do this for me. Whoa. Take the partial of this with respect to y. This one. What do you get?
So just get yeah.
Yep. And 3y squared over 3.
Yeah.
And you get ax squared minus ay squared. Right. Yep. Okay. Good questions. I like it. See how math is fun? It is.
It is fun. Early, yeah.
Okay, step 2.
Break that and do it really good. It's really off that.
We're going to derive or take the differentiate. We will get there, Sam. Step 1 with respect to x. So let's see how well your partial with respect to x of that one is. Yep, yep. So partial of this with respect to x. What do you get? 2a xy. Yep. Then what? Almost. F prime of x. Bingo. Because it's a derivative, right? It's a derivative of whatever this function is. Questions? Okay. Step 3.
Wait, I said.
Oh, sorry.
I know, right?
Sorry.
Yes, is there any question?
You just tell me. Yes. I have a question. Hold on. Where are you?
No, I was.
Oh, wait. Well, we could, but we're not going to.
That'd be 2axy. If you derivative with respect to x.
Yes, that is a 2.
Yeah, but you want to do 2ay.
No, because
No, because x is squared.
Oh, we're taking the.
Of
Yeah.
that one. Yeah,
Yeah,
see,
the
step 1 with respect to x.
Why?
No, F.
Are you asking WHY?
Yeah, WHY.
Because these are the steps to do this. That's
So
why.
what was the point of having the first equation?
Huh?
What was the point of what was the point of having that second equation?
Oh, I gotta.
We're here. I haven't written yet.
Okay.
This is like finding b in differential equations.
Yes.
Like, this is-
To be honest, this is easier than doing it the other way we did it before.
Sure.
It is. Have we done anything strenuous? Did I say
Strenuous?
Strenuous? Yes.
I mean, yeah.
Step 3. Compare the V equation with step 2, right? Does everyone see that? Because we already have that, right? So we say, so let's do this first. It was 2axy, right? Equals 2axy plus f prime of x.
Prime is not,
What does that tell us?
that prime is 0.
F prime is x is 0.
Like, this is the first time I've seen this part of differential equations actually used ever in my life.
Okay.
Why do you know that though?
How do I know what?
I spent so much time on
Prime
this.
is 0.
Bring this over. That's a negative, right?
Oh, you saw
Algebra.
He's smart. I like it.
So we're doing step 3 to find f prime of x. And then what do we need to find f? We integrate, right? Oh, f of x is constant. What happens if it wasn't 0? Then you'd integrate and you would find that this would be a function of x.
Which doesn't make sense.
And what do you think step 4 is? Yep. Now plug plug in f of x into step 2, I think, because we already have what psi is, right?
Yeah. Yeah, step one is just
Ax squared y minus a y cubed over 3, is that right? Plus a constant.
that's the first time I've ever seen actually finding phi as a useful thing.
Oh, good. I like that. And look, this is your streamline. And how do you get the different streamlines? You change.
Now, would your constant, like, would that change your level, or would it just change the streamline in general?
It would just change the location where your streamline
Yeah,
is.
that's what I was
That's,
thinking,
yep.
kind of it.
Yep.
So at a certain point, it will be a straight line, and other times,
Yep.
It makes sense, I just took a while.
So there's, and this is how the homework, they did this in the solution. They did these steps. So
Number 3.
I think it's number 3. Yep. But it is a little tricky, so that's why I wanted to give you the solution, so you can look at it and do it. And then I want you to plot, okay?
it's really not that long a process. It's just two partials. It's just, yeah, when you have to, like, overwhelm it, it takes, I feel like you took the APQ, yeah. Yeah, there, you know.
That's
No,
I mean, I get it, but
because it's just my equivalent number, everything is how it was, you know. You have to know that you two partially equal each other and then find out the original.
just super more like everything. Yeah, twisted tea.
So what we did is we had a profile of your x velocity or u velocity in v, and we said there's a new way to find streamlines, and we do the stream function, which is psi. It's actually a shorter method, but there's 4 steps. But it's like you just kind of take you do the integration, and then you take the derivative, and then you compare, and then you finally plug it in. Okay?
Now,
Yes.
how do you know that's right?
How you know? You could take the partials of this with respect to x and y and see if you get back to
No, you can't.
those.
You don't.
You should.
Well, you can, but there's no constant.
Oh, it'll go away, right?
Yeah.
No way. No.
No, I mean like in the bottom one there. See, there's a plus c.
Yeah.
You don't get that plus c.
Wait. So you're. What I was saying is, you take this,
Take the, yeah, take the derivative of that.
and then you take. There would be 0 for c. That's a good question, though. How would you check the c? Yeah, you just take the partials of psi with x, and you should get back to those original equations that we had before. Because what is d psi dx?
Yeah.
Should be v, right? Is that what we defined it?
Yeah.
Yep. Or negative v, yep. And then d psi dy is u.
But Doc, did the V equation really like matter that was given to us? Because we didn't really use it, but we use it to check ourselves.
We did use it. We needed it to find f prime.
Yeah, if you didn't have that, you never.
Step 3.
Oh, okay.
Because you compared that. Good. Okay. Let's take a 5-minute break. Then I'll talk about momentum, Navier Stokes, and we'll probably do one practice problem, and then I'll review everything on Thursday. Okay? To Shane's question about, remember why you said, why is it out?
Yeah.
Mine's in?
Yeah, yeah.
Well, I figured it out.
Oh, really?
It just dawned on me the other day, actually yesterday in dynamics. I'm like, oh,
Actually,
that's,
yeah.
yeah. So here's a dragster. Thank you. I couldn't think of it. And it's going to the left. So when you have thrust, the thrust actually is the same direction that you're moving.
Right.
Okay. And drag force is opposing.
Yep.
So when you do the sum of the forces equals all of this. This is the fluid linear momentum one. Here, we already know that thrust is going that way. So if we just do sum of the forces equals ma, right? So we have T minus FD equals ma. You notice how T is positive.
Yeah.
All right, so now we're going to do it this method. Okay? So we have what? Minus FD equals ma, and then there's only one out, right? So plus m dot times what? The direction, what's the direction of the fluid? Negative. So when you bring it over, you get positive T. Okay? Okay? So I've added this in my notes.
It's just because of yesterday.
It was. The light bulb went off. I was like, huh. I
Yeah,
think
this
I
is the-
remember to answer Shane's question.
The
Yeah,
only
but the
thing I
thing
know
is,
that it's
thrust
outlined
goes
is-
the opposite because
No, actually-
aren't you moving forward because of thrust going backwards.
Yeah, that's why thrust is that way. Because the fluid is spitting out that way,
Yeah.
causing you to move
But
that
the
way.
fluid is what is making.
The fluid, see, the fluid here is this case. The fluid is actually going in the opposite direction that you're moving.
In reality, it's the engine.
It's the engine, yeah.
But like,
So in an airplane, if you're
You still put it as an arrow that's being pulled.
Yeah.
You know, like, it's the same
Yeah.
concept as that. It's
So
the
the-
exact same concept.
and when you do airplanes, the thrust is the vector same direction that you're moving.
so why did it? But there was one part when we were doing thrust was either here or dynamics that we put in the opposite direction.
Was it here?
In this class, what we don't use, like when we did the satellites, thrust was opposite direction of motion.
Thank you.
Oh, we.
Now when I'm explaining what it is.
Yeah. Yes. When we bring it over, it's because there is no external forces, so we didn't have to worry about the sign on that. Oh, yeah, the sign would go away. So okay. So that was just a side note. So let's take the equation we know and let's write this in differential form, like we did the mass, okay? So what type of forces do we have? Well, we have body and we have surface. And then we write this like this. And I'm going to keep them like this. Just like we did mass. So
This is that there.
this is exactly what this is, yep. And hopefully you notice here we have what is rho times V, mass, and then mass over time gives us, that's flow rate, oh sorry, that's mass, and then basically dV over dt gives us acceleration, okay? So this is the same as this. Okay, and that's your control volume. So that's basically mass times, that's your inertia of whatever is moving. Okay. So I'm not going to get into too much detail, but I will have a video that I'll post online. Okay. You see these terms right here? What do you think you got to do with those terms that we did with mass? You got to look at what's coming in the x direction for momentum going out, okay? And then what does this term kind of approximately be? So I'll put here, similar to analysis. Oh, I didn't spell that right. Of conservation of mass, but there's a lot more terms, and the video I'll post you can show that. And then this right here is approximately this. And how many, again, these are all vectors. Oops, sorry, I should have put vectors on these. And this one too, I missed that. So what does that mean? There's how many directions for forces? 3. So there's 3 sets of equations. That's why there's 3 sets of equations here, x, y, and z. Okay, so you have to look at every direction.
Could you explain the left side? Because those are
This side?
Yeah.
Oh, I'm going to cover that here in a second, just briefly. But the forces acting on the body you have, or the actual system that we're looking at, body forces, and then you have surface forces. And I'm going to get into details more of that. Okay.
And the right side is really just
Is
mass and acceleration right there.
that's mass times acceleration, and that is your linear momentum in and out. Yep.
Is this supposed to say Z direction, or Z component instead of W component on the paper here? The one with the three of them has X component, Y component.
Oh yeah, that should be Z. Yep. I didn't even catch that. Thank you. Did I do that down below too? No. Yep. I should say Z. Sorry. On these, on the third one, should say Z component, not W component. So, let's see. We got time. Actually, maybe I'll do those practice problems Thursday. Body. I'm going to do X direction, Y direction, and Z direction. Tell me in differential form, or I guess the easier way is, what is gravity force?
That's why.
This is Fxg. Mm-hmm. It depends. It depends on, like, if you remember, like, just think of cars at an angle, right? It depends on the angle that you're looking at, okay? So we have rho gx dx dy and dz. What does this give you right here? Volume. So volume times density gives you mass, and that times that, okay? And you could do the same for these. Yep. But now we're writing in differential form, yep, which is slightly different. So body is just your gravity terms, okay? Surface. What type of surface forces do we have?
Drag.
What's drag based on?
Surface.
Friction.
Okay, yes. Can you go even deeper?
Shape. Temperature.
Sorry, what did Nate say?
Shear.
No, you're just thinking of pure surface tension.
Can you say it louder, Tyler?
Shear and pressure.
Yeah.
You're a cheater. You do that.
Well, I wrote it down for a reason.
So pressure is the reason why we have drag, right? Viscous is friction, surface friction, remember? Viscous forces. So you have viscous, which is surface forces, and then you have pressure. So pressure is normal, right, to the surface? And what's viscous? Or shear? Tangential. So I don't know if you've seen this, but here's a 2D. So here's a 2D, and you have your pressures, which are normal, and then you have at each surface tangential. So the way we do this, let's just write this so you've seen it. Yep. Yes, these are Z's. Yep. Because this is what they call, this is multiple forces, we can write it in like a matrix form.
These represent surface forces?
Yep.
Surface.
And to be honest, I don't remember right off my head why there's a negative.
The matrix is for a three-dimensional web, not there's not the box we're looking at. If you have a C.
This is, yeah, this could be the box.
Yeah.
Yeah, it's the same rectangular box that we're looking at for conservation of mass. Yep, you can do that. Yep. I have to get back to you Thursday why there's a negative here. I don't remember off my head. Sorry. So these terms right here are our pressure, and this is our shear forces. Okay.
If it was a negative pressure, like in a vacuum, wouldn't those all be positive then?
I don't remember.
Okay. Just a random.
Yeah, I don't remember.
It just seems like that would make sense since all the pressure is going towards the surface. But that's why it's negative.
I gotta look it up. I don't remember. Okay, so you have viscous and pressure. So here's our pressure, here's our viscous. You see how I wrote, like, these are pressures. We know these. These, there's a whole bunch of derivations for those. But what we can do is they write this in terms of something else. So this will be the last thing we write, and then I'll stop today. This one's a little bit long. Oops. Make this bigger. So what we do now is, if we go back up, I'll come back down. Go back to this one. Over here on the right, these blue, if you do those, momentum coming in and going out, like we did with conservation of mass, you'll get a set of equations that you can combine, okay? Then you add it to this term, and then in each direction in the x, y, and z, you have a whole set of equations. So basically what you do is you fill back into these equations, and you end up getting these three sets of equations on your sheet. Okay, so after a whole bunch of algebra, you could do that. All right, the video I have that I'll post, I'm pretty sure does the x direction for you. So you can kind of see where that comes from. All right, but in the sense, now we have differential form for conservation of mass and momentum, which are forces. So we can figure out anywhere in the flow what some of these values are. Okay, so on Thursday I'll review and we'll do these two practice problems. Okay, so the first practice problem, you have two parallel plates. One's moving at the top, and then the next one is what? You have a pipe flow. Okay, we can figure out the exact flow and distribution of those. Okay. All right, so again, I know it was a lot of math, a lot of weird things you probably haven't seen, but just to kind of give you an idea of how we would actually do this, okay? So let me hit pause here.